Hi, this is an example problem on airplane lift. This comes from chapter 11 on ideal fluid flow. Pause for a moment to read the question. Okay, so in this case we've got an airplane. We're given the mass, we're given information about the area of the wings, and we know what the density of air is here. In part A it asks, what is the pressure difference between the lower and upper surfaces of the wings? So to understand how to try to answer this question, we're going to start by doing a free body diagram of the airplane itself. So let me just represent the airplane as a dot here. And we know that we have a force of gravity that is directed downwards, Fg. And we know that we have the mass of the airplane, so we can calculate the magnitude of the gravitational force. Going to be the mass of the plane times gravitational acceleration constant. Next, what do we have that balances that gravitational force? Well, it's got to be the lift, and we can see the lift is drawn in the picture there. And so we've got an upward force, F. What do I want to call this? Lift, I guess. And we know that this thing is balancing the gravitational force because we're told that the airplane is in level flight, which means it's not moving up or down. It's not accelerating up or down. The acceleration is 0, in other words, in the y direction at least. Now, in this case, and notice that we're ignoring anything in the x direction. There's some drag, etc. There's some thrust force, etc. We're going to ignore all that stuff because we're trying to focus just on the lift and how it balances gravity. So maybe better to do would be this. All right. So to figure out what the lift comes from, we got to consider that there's air on the bottom and air on the top of the wing, and that's going to cause the pressure of that air is going to be pushing on the area of the wing. Now we assume the area on the top and bottom is the same. However, because of the speed of the fluid, above and below are different. We're going to have different pressures. Now we know if we consider the lift at the lower surface, right, it's going to have to be a lot bigger than it is at the top surface, right? So this is this lift at the bottom. We're going to call this, we can write this as the force for the lower surface, and that's going to be equal to the pressure times the area of the wing. So the pressure at the lower surface times the area of the wing, and at the top we've got an upper force pushing down on the wing, and that's going to be the pressure on the upper surface multiplied by the area of the wing. And notice that the lift force is the difference of these two, right? So if I want to write down what the lift force is equal to, F lift, it's going to be F lower minus F upper. And ultimately, we can go ahead and put those equations in that we just wrote down. So F lower is the pressure at the lower point times the area of the wing minus F upper, the pressure above the wing at the upper point, times the area. And if we want, we can factor the area out because we're going to assume that the total area of the wing is the same above and below. So we get an expression here, PL minus P upper multiplied by A. All right, so for part A, we can go ahead and use Newton's second law to relate the lift force to the weight, the gravitational force, and then solve for the difference in pressures, PL minus PU. So if we think about this as Newton's second law, which is going to tell us that the acceleration, the mass times the acceleration in the y direction, going to be equal to the sum of all the forces in the y direction. Now we know the acceleration is 0 in the y direction, and that these forces are going to sum to 0. And the two forces we have are the upward lift force, which we can write as PL minus PU, as we just saw. And we have the downward gravitational force, which is going to be plus or minus mg. Now when we go ahead and do some algebra, we'll see that we can write this as PL minus PU times A is equal to mg. And finally, we can divide by A on both sides to solve for the pressure difference between the upper and lower portions of the wing. And so in this case, we are going to put in the mass of the plane, 8.66 times 10 to the 4th kilograms. We're going to put in the gravitational constant, 9.8 meters per second squared, and we need to divide that by the total surface area of the plane, which is equal to 90 meters squared. When we put that into the calculator, we get a value here. PL lower minus P upper is equal to about 9,430 newtons per meter squared. Or we can write this as pascals if we want. So that's the answer to part A. Let's look at part B. Part B asks us, if the speed of air under the wings is 225 meters per second, what is the speed of the air over the wings? Well, in this case, what we're looking at is the flow of the air, and so we're going to use the equations for ideal fluids here. We can go ahead and label these points. Let's say this point here on top. This is your upper, I'm just going to call it U, and below you've got your lower, so two sections of the fluid. And it does say, looks like I already highlighted this, ignore any height difference between the lower and upper surfaces of the wing. So, for example, we're going to use Bernoulli's equation to relate these speeds because we already know the pressure differences. However, Bernoulli's equation, if we look at it, it also involves the heights, right? So that can also have an effect. In this case, however, we're going to ignore that because the height difference here, call that h, if you will. You get something with rho g h in the Bernoulli equation, but here rho is so tiny, it's not going to have, it's completely negligible compared to the difference in pressure due to the speeds. So we can completely ignore that, as it says in the problem. All right, so in order to use Bernoulli's equation, let's go ahead and see how we might write this down. So Bernoulli's equation tells us this. It tells us that we can write two sides that are equal, and there's three terms, three terms for each point. And so here we've labeled the points 1 and point 2. You can see them here. In our problem, we've labeled them L and U, and we can go ahead and write down this equation just as it appears. Notice that it looks kind of like kinetic energy, looks kind of like potential energy. What we've done here is we've changed the mass for rho in this equation, and also be careful not to confuse capital P, the pressure, with lowercase rho, the density of the fluid. So let's go write this down for our problem. We've got P lower plus 1/2 rho g, oops, that's not right, 1/2 rho VL squared plus rho g YL is equal to, same stuff now for the upper, P upper plus 1/2 rho V upper squared plus rho G Y upper. And of course, as we said, we're ignoring any difference in height, so we can cancel those out. Now, what we want to do here is try to identify in the picture what things we know. So V upper is up here. V lower is down here. And we're given the speed of the air under the wings, so lower, don't get that confused with upper. The lower speed here is 225 meters per second. The upper speed we don't know. Now the pressures, right, we've got pressures that are below and above, so we've got your P upper, got your P lower. We don't know those individually, however, we do know what the difference is, so those are known in a sense. Going to Bernoulli's equation, we can go ahead and relate those a little bit. So let me do some math here. I'm going to go ahead and subtract the PU from both sides, so that's going to be gone here. And let me go ahead and write this. I guess let's see, we're solving for the V upper, so let's leave this here as plus 1/2 rho VL squared is equal to 1/2 rho V upper squared, right? And so to solve for V upper, we just need to do a little bit more work here. Let's go ahead and rearrange this equation, all right? So this is going to be 1/2 rho V upper squared equals PL minus PU, put that in parentheses, we know that number from part A, plus 1/2 rho V lower squared. Now let's go ahead and multiply both sides by 2 over rho. Notice I gotta get the whole thing, 2 over rho. Cancel these out here. We'll get V upper squared is equal to the whole quantity, PL minus PU, plus 1/2 rho VL squared multiplied by 2 divided by rho. And finally, we're going to take the square root of this whole thing here. So we can square root this, and we're left with VU, exactly what we want to calculate, right? All right, so putting in the values, VU is equal to the square root of, first we're going to put in PL minus PU, which is this number, 9,430 newtons per meter squared, plus 1/2. Got to look up the density of air, which is the fluid here, 1.29 kilograms per meter cubed. Multiplied by V lower, which is the number we were given. (225 meters per second). Squared. All multiplied by 2 divided by rho, which is 1.29 kilograms per meter cubed again. So we can go ahead and put that into the calculator. And when we do that, we're going to get a value that comes out to 255 meters per second. And so that's the answer for the speed of the air across the top of the wing. Again, notice that the speed across the top of the wing, it's greater, 255, lower down 225, and it's the higher speed with Bernoulli's equation, which produces the lower pressure. Now, part C is asking us, explain while all aircraft have a ceiling, a maximum operational altitude. So this should say Y. So it's true, beyond a certain height, if you go up too high, you're not going to be able to get enough lift to keep you up. Why is that? Well, we can go back and look at this equation right here. Let's look at this one. Let's focus on this guy for a second. So for part C, if we look at this, we can find that if we do a little bit of algebra, it's this pressure difference PL minus PU, which is required to support the weight, right? And if we go ahead and do a little bit of work here, subtract the term 1/2 rho times V lower from both sides. And then we can go ahead and take one more step here just to simplify this a little bit more. And we're going to end up with, let's factor out the 1/2 rho. So we've got a rho over 2 multiplied by the quantity V upper squared minus V lower squared. Now, as you go higher, what happens to rho? As rho goes higher, the air gets thinner, the density goes down, and that's going to cause this pressure to get smaller. And so once you get too high up, the air's too thin, you won't have enough density to be able to generate a big enough pressure differential to support the weight. You might have recently heard about the mission to Mars, where they've been able to generate lift with a drone there, and in that case, they need to go extremely fast with the propeller because the density is like 1% of the Earth's atmosphere on Mars. So by making the propeller go extremely fast, they can get a larger difference in the speed of the fluid below and above the propeller, and so that's required to be able to make that drone work on Mars. They also make it extremely light so that this pressure difference doesn't need to be so big either, because the weight of the drone is not that large.